Hi there. This week we're going to be looking at integration. First we're going to look at integration of common functions, for example exponentials and trig functions, and then we're going to move on to look at integration by substitution. So first of all, what is integration? Well, integration is essentially the opposite process to differentiation. So first let's look at standard integration. So let's say that we want to integrate a standard polynomial function, which is represented here as y being equal to the integral of m times x to the power of n dx. So m is just some arbitrary coefficient, some arbitrary number. N is the power of x, and then dx at the end means that we are integrating with respect to x. So how exactly do we integrate? Well, essentially we're going to do the opposite to what we would do for differentiation. So for differentiation we would multiply by the original power and then minus 1 from the power. But for integration we add 1 to the power first and then we divide by the new power. So y here is then equal to m, that coefficient, times by x to the power of n plus 1, and then the whole thing is divided by n plus 1, that new power. For integration we also have this plus c, which means that we have to add a constant on at the end of our final answer, and that's because we don't have any upper or lower limits to that integral. So it's an indefinite integral, so if you have no upper or lower limits you have to add c, a constant of integration, to the end of your final answer. So be careful not to forget that. So let's look at an example where we have y is equal to the integral of 6 multiplied by x to the power of 4, and we're integrating with respect to x. So y is then equal to the integral of, well, the 6 just stays the same, and then the integral of x to the power of 4 is just x. The 4 becomes a 5, and then we divide the whole thing by the new power of 5. Don't forget to add on at the end our constant of integration. So that is our final answer for that example. So now let's say that we want to look at an example where we have y is equal to the integral of 6 divided by x to the power of 4, and we're integrating with respect to x. So to be able to use the sort of standard rules of integration, we have to be able to write our example in this form where we have y is equal to the integral of x times x to the power of n. So essentially what we have to do is say that then, okay, we can write y is equal to the integral of 6 multiplied by x to the power of minus 4. So we're bringing that power up the top and it becomes negative. So we can then apply that sort of standard rule of integration, and that means that we have y is equal to 6, stays the same, and then the x to the power of minus 4 becomes x to the power of minus 3 because we add 1, and then we divide by the new power of minus 3, and then we add on our constant as well, don't forget that. So if we tidy that up, essentially what we can write is that y is equal to minus 2 divided by x to the power of 3 plus c. So we take our negative power on the top line down to the bottom line because we like to have positive powers in our final answer. Okay, now let's look at integration of exponential functions. So before we think about integrating an exponential function, let's first think about how we differentiated an exponential function. So if we had an exponential function of e to the power of ax, and then we were asked to differentiate that, then what we did was that we multiplied the entire term by that coefficient of x, a, and then the actual power, ax, that just stayed the same, that didn't change. So what if we were looking at integrating exponentials? Well, if we have y being equal to the integral of e to the power of ax, remember that e is just a mathematical constant, and we're integrating with respect to x, then what happens is that now we actually divide by this power a. Okay, so instead of multiplying, we now divide, and the actual power itself, that just stays the same, that doesn't change, it's still just ax. Don't forget that we also add our constant of integration on to the end as well. So if we look at the example where y is equal to the integral of 4 times e to the power of 4x, and we're integrating with respect to x, then y would be equal to, well, the 4 is just a constant, so then we essentially just have e to the 4x because the power stayed the same, and then we divide by this coefficient of 4 here. So don't forget to add on the constant as well. So what happens is this 4 cancels with this 4, and the final answer is just e to the 4x plus c for that problem. So you might now think that we're going to look at integrating natural logs, but we're actually not going to look at that at the minute. It's actually a little bit more complex than you might think. What we are going to look at is integration that results in natural logs. So if we have y is equal to the integral of a, so a is just some arbitrary number, some constant, divided by x, and we're integrating with respect to x, then our answer for the integration is that y is going to be equal to a, that coefficient, multiplied by the natural log of x, and then we also have our constant of integration as well. So let's look at an example where we have y is equal to the integral of 4 divided by 5x, and we're integrating with respect to x. And basically what we can say is that a here is equal to 4 over 5, so we can say that y will then be equal to, for integrating that, then it will be 4 over 5, the natural log of x, plus c, our constant of integration. So it is as simple as that. So now let's look at something a bit more complex. So let's say that we're trying to integrate something that is essentially the differential of a function of x divided by that original function of x. So basically we have f dash x on the top line, and then the actual function, original function, f of x on the bottom line. So if we want to integrate that with respect to x, then what we find is the integral is just equal to the natural log of f of x, so the natural log of the thing on the bottom line. And then to that we then add our constant of integration as well. Let's look at an example where we have y is equal to the integral of 12x divided by 3x squared plus 4, and we're trying to integrate that with respect to x. The first thing that we should be thinking about is saying, okay, well, let's say f of x then has to be equal to 3x squared plus 4. So that means that f dash of x has to be equal to, well, the 2 comes down to get multiplied by the 3, and the x squared just goes to x, and then the 4 disappears. So in order for us to sort of use this sort of rule of integration, what we can say is that y is equal to the integral of 6x divided by 3x squared plus 4, but in the original example we have 12x, so we have to account for that 12. So essentially what we do is we say that, okay, so if we multiply that 6 by 2, then we get our 12. So that's an equivalent way to write this sort of expression for y. We can then actually use these rules to integrate, so we can say that y is then going to be equal to the natural log of the thing on the bottom line, which is 3x squared plus 4, and then we have our 2 at the front, and that's just a constant, it stays the same, and then we have our constant of integration as well. So that's the final answer to that example problem. Okay, so moving on, let's look at integrating trig functions. So first we'll look at integrating sine functions before we move on to cosine functions. So how did we differentiate sine functions? So when we have sine of ax, for example, where a is just some arbitrary coefficient. Hopefully you remember that what happens is that when we're differentiating, we bring that coefficient a out the front as a multiplier, and then the sine function changes to a cosine function, and the thing in the bracket just stays the same. So what happens when we integrate? Well, let's say that y is equal to the integral of sine of ax, and we're integrating with respect to x, then that means that y is actually equal to minus 1 over a cos of ax, and then you've got your constant of integration. So now when we're integrating, what happens is that the coefficient a of your sine function comes out the front, but now as a divider instead of a multiplier. Also, the sine function changes to a negative cosine function. So when we're integrating sine, you get a negative cos, and then the coefficient of x inside the bracket comes out the front as a divider instead of a multiplier, and again the thing in the bracket just stays exactly the same. And again, don't forget the constant of integration. So let's take a look at an example where we have y being equal to the integral of 4 sine 6x, and we're integrating with respect to x. So if you want to use this rule above, we can say that y must be equal to, the 4 is just a multiplier, so that just stays there, and then the sine goes to a negative cosine. The thing in the bracket, 6x, just stays the same, and then we can't forget to divide through by the coefficient of x, which is 6. Also, we can't forget our constant of integration. We can then just tidy that up a little bit, and we can make equal to minus 2 over 3 cos of 6x plus c. Okay, and that is our final answer for that problem. Now let's look at integrating a cosine function. So before we actually look at integration, again let's think about the differentiation. So what did we do for differentiating a cosine function? Hopefully remember that if you differentiate a cosine function, then again we bring the a out as a multiplier, as we did for sine. So the coefficient of x comes out as a multiplier, but now the cosine function goes to a negative sine function. Okay, and again, the thing in the bracket just stays the same. Now let's think about integration. So for integration, if we want to differentiate y being equal to the integral of cos ax with respect to x, then that means that y would be equal to 1 over a, the sine of ax, plus c. So as was the case for the previous integration of sine function, the a comes out the front but now as a divider instead of a multiplier. And the cosine function now goes to a positive sine function. Okay? And again, the thing in the bracket just stays exactly the same. And we have our constant of integration. As an example, let's say that y is equal to the integral of 5 cos of 2x, and we're integrating with respect to x. So if we use the rule stated above here, then we can say that y is going to be equal to, 5, that's a multiplier, so it stays where it is for the minute, and then the cosine goes to a positive sine function. The thing in the bracket then again just stays the same, and we can't forget to then divide through by the coefficient 2. And we can't also forget to add our constant of integration. So we can't really take out any common factor there, so that would be our final answer for that problem. Before we move on to look at integration by substitution, I just want to take a quick look at definite integrals. So what we've covered so far, we've had indefinite integrals where we have no upper or lower limits to our integration, and so we have to add a constant of integration, c, onto our final answer. But in definite integrals, we essentially have upper and lower limits of integration, so we don't need our constant of integration anymore. So I'm going to look just now at standard integration to show you what I mean by a definite integral, but that can actually, definite integrals can apply for any type of integration. So for example, exponential, trig functions, integration by substitution. Well, for now let's just look at standard integration. So now we want to integrate m times x to the power of n, but we have an upper limit of integration b and a lower limit of integration a, above and below the integral symbol. Again, we're integrating with respect to x. So our integral is then, as before, equal to m times x to the power of n plus 1 divided by n plus 1. So we add 1 to the power and divide by the new power. However, what we should do now is write that in a sort of square bracket and then put our upper and lower limits of integration sort of at the top and bottom of those square brackets. What this then means is that we're going to first substitute in x is equal to the upper limit of b, and we put that in a nice curly bracket, and then from that we are going to minus the function where x is equal to the lower limit of a. Again, we put this into curly brackets. The main reason I use these sort of square brackets and then curly brackets is just so that I don't get muddled up with what I'm doing. So let's look at an example where y is equal to the integral of 3x cubed with respect to x, and we have an upper limit of 2 and a lower limit of 1. So what we can say then is that y is equal to, well, the integral of 3x squared would be 3x to the power of 4 over 4. And then putting that into the square bracket, we have an upper limit of 2 and a lower limit of 1. So we can then say that we are going to have, open your curly bracket, 3, and then we'll let x equal 2, the upper limit, to the power of 4, divided by 4. And then from that we're going to minus 3, and now we'll let x equal to the lower limit, 1, to the power of 4, divided by 4. So 2 to the power of 4 gives you 16. If we multiply that by 3, we get 48, divided by 4. From that we minus 3 over 4. So our final answer is either 45 over 4 or 11.25. So now our final answer is in the form of a number, and we don't need any constant of integration. Okay, so that type of approach can be used for integration of any type of function, where we have an upper and a lower limit. So the last thing that we're going to be doing is now looking at integration by substitution. So integration by substitution is kind of used sort of where the chain rule is used for differentiation. It's used when we're looking at a function within another function. It is sort of best understood by looking at an example. So let's say that y is equal to the integral of the sine of 4x plus 2. And we're integrating with respect to x. So what we're going to do, the first thing that we're going to do is say, okay, we'll let the internal function, the 4x plus 2, which is inside the other function, we'll let that equal u. So u is equal to 4x plus 2. So to make things simpler so that we can use the sort of standard rules for trigonometry, we can then say that y is equal to the sine of the integration of the sine of u. But now we can't integrate the function of u with respect to x, we should be integrating it with respect to u. We can't just change dx to du, we have to sort of find the appropriate relationship between du and dx. So what we can say then is that here du by the x, to the differential of u with respect to x, is equal to 4. If we differentiate u with respect to x, we just have 4. So then we can say that dx then must be equal to du divided by 4. Okay, so instead of dx here, we now have du divided by 4. So we can then actually write that y is equal to 1 over 4 times the integral of sine u du. So we're just taking the 1 over 4 outside the integral. If we want to integrate a sine function with respect now to du, hopefully you'll remember that if we integrate a sine function, we get a minus cosine function. So y is then equal to 1 over 4 times by the integral of sine u with respect to u, which is minus cos u. And then don't forget your constant of integration as well. The last thing that we really need to do before we get our final answer is to then substitute the expression for u back in. Okay, so don't forget to do that as your last step. So what we end up with is minus 1 over 4 times the cosine of u is equal to 4x plus 2, and then your constant of integration. So that is our final answer for that problem. Before we finish up, let's just take a look at one more example of integration by substitution. So here we have y being equal to the integral of 3x minus 7 to the power of 5. So again, we're going to let u equal the internal function, so the thing inside the bracket, which is 3x minus 7. We can then say that if we want to differentiate u with respect to x to get du by dx, that's just going to be equal to 3. And then we can write that dx must then be equal to du divided by 3. We can now then write y in terms of u rather than x. So we can say that y is equal to the integral of u to the power of 5, and in place of dx we have du over 3. So before we actually perform the integration, we can just make things a little bit simpler by taking the 1 over 3 outside, and then the integral of u to the power of 5 with respect to u. So if we use the sort of rules of standard integration, then we have to add 1 to the power and then divide through by the new power. So we get a third times u to the power of 6 divided by 6. And again, we have to add our constant of integration. You then have essentially 3 times 6 on the bottom line of the fraction here, so that becomes 1 over 18. And in place of u, you have to substitute back in the expression for u, which is 3x minus 7. That's now to the power of 6. And you have your constant of integration. So y is equal to 1 over 18 times 3x minus 7 to the power of 6 plus c. So that's our final answer for that problem. So that's the general process of integration by substitution, and you can apply that to quite a wide variety of problems. So we've looked at some general rules of integration, and then we've looked at indefinite integrals and definite integrals, and then finally we looked at integration by substitution. So that's all we're going to look at today, so thanks for watching.